Hey everyone, how's it going? So as I just said, today we get to meet the emote. This is Shadow. He's our biggest ferret. He's long boy. He's really sleepy though, so I don't want to. He just woke up. I woke him up just to show him off. So if any of you have never seen a ferret before, they're basically cat snakes, as someone in the chat just said. You can twist them and turn them. They're super cute. We have one more ferret. Her name is Pixel, but we'll be waiting to show her off later. Hello. All right, so just give me 1 second. I'm gonna go put him back outside so he can go back to sleep. Cool. So you've seen a ferret. We'll incorporate him more into the lectures a bit later in the course. So let me bring over the programming here. So this is the course sheet. Just wanted to make a few notes about this. So what I've done is I've also added links to the lecture slides. So now you can just click here and just open the lecture slides directly for that lecture. And as I said before, these are given out as PDF. So I gave the actual slides are done with PowerPoint, but the slides that I give to you are PDF because the PowerPoint slides, those files are a little bit big. Also, I'm not sure if anyone knows the exact answer to this, but I think that the Twitch VODs are going to be disappearing soon. I think it's between 2 weeks and a month or something like that they get stored for affiliates. So if at some point, if you've been watching the VODs here on Twitch, at some point I think that these VODs are going to break. But I'm not sure exactly what that point is. So you can still watch the YouTube lectures. Those will stay there forever, hopefully. And the super forever is that you can download the lecture directly from my website. So the links are there as well. All right. So on Tuesday, we went over some C++ coding examples. And we also went over assignment 1. So today we're going to get really into the meat of the course. This is really where the course starts, right? So we had to do a lot of explaining about C++ and SFML in order to get to the point where we can start programming in it. And now we're going to really start talking about the meat of the course. So someone in the chat just said, what's the best way to access the YouTube videos? I looked at your channel and couldn't find a public playlist. So right now, the only way that the public can see the videos are through Twitch. I may release a public playlist afterwards, maybe when the course is done on YouTube. But for now, you can go to the Twitch videos part, and the past lectures will be there on Twitch for now. But you kind of have to keep up with that because they're going to disappear eventually. And maybe after the course is done, I can talk to the university and allow the YouTube lectures to be permanently online and publicly available. Cool. All right, let's get into the lecture for today. So we're going to do some lecturing, and then we'll do a little bit of live coding at the end as well. And again, let me just go back here. So assignment 1 was released on Tuesday. Assignment 1 is due a week from now, so next Thursday. On that Thursday, we will be talking about assignment 2. And so all of the stuff in this lecture and the next lecture are going to be the things that you need to know to do assignment 2. And we'll be all the stuff we talk about today, so ECS and the Vec2 class, you will be implementing that for assignment 2. And also in the next class, we'll talk about the entity manager, and we'll go over some basic some linear algebra that we'll need to know to do assignment 2. And I'm sure that you've all done that already, but just for those who need a little bit of a refresher, we'll be doing a little bit of that as well. Okay. So with that in mind, for the context of that's what we're doing, let's get into that lecture. So here we go. All right. So technically this is lecture 5, right? Okay, let me change that. Lecture 5. Is that correct? Yes, it is lecture 5. Okay. So, welcome to lecture 5. Today we're going to be talking about entities, components, and systems. So we'll be talking about ECS, which is the whole point of this course is game programming. So far, we really haven't done any game programming, right? So it's almost 2 weeks in, and now we're starting the game programming. At the end, we'll also talk about a Vec2 class, and I won't talk about that now, but we'll get into that at the end of the lecture, and then we'll live implement part of that Vec2 class, and that is something that you will have to complete when it comes to assignment 2. So ECS game programming, what the hell is it? Now, some of these slides are a repeat from the very first lecture, but I want to get you all caught up to speed. So why do we use ECS for games? Why is it a good programming architecture? Well, again, ECS stands for entities, components, and systems. An entity is absolutely any object in the game. So whether it's a player, it's a platform, it's a tile or a bullet or whatever, if you can see it in the game, and even some things that you can't see, those are all entities. And so ECS is a software programming paradigm. It's called a compositional-based software design. And it will allow us to really easily implement games and game logic, and it'll be really cool, and we'll see that going forward. So just to review again, in order to know why ECS is important, we want to look at object-oriented design and then compare it to object-oriented design. So, object-oriented programming and object-oriented design, what is that? Well, you've all had a course in that. The people who are not in the class who are watching may not have, but it's a prerequisite to the course to have that. So you know all about object-oriented programming. So how would we design a game that looks sort of like this? Let me get my pen out. So sort of like this with things like tiles and players and backgrounds and stuff like that. Well, if we were doing that with object-oriented design, what we would have is that every entity in the game, so an entity would be any object, right? If we want to use this same analogy for entities being any object, then what we would do is we would use entity as a base class, and then we would have derived classes from the base class, right? So for example, every entity in the game might have an XY position. And so what we would have is we'd have a base class called entity that would store an XY position. Then we might have a class which is like a tile. And then we might have a class which is a player. And what would happen is that those tiles and those players would inherit from the entity class. And so what we end up having with that architecture is something like this. So we have the base class entity up at the top. So this is the base. Still no good at drawing with a mouse. Then from that base class, we are going to derive different types of enemies. So for example, maybe we have the player, right? Maybe we have some types of entities that can move around, and we'll call those dynamic entities. So maybe we have enemies which are dynamic, and maybe we have players which are dynamic. Also, maybe we have static entities, like we have a tile, for example, right? So in the tile, maybe that doesn't move around, and so we would call that like a static entity. So we could have rocks or trees. And so what happens here is we need to have a class, basically, for every type of entity in the game, and that's going to be really cumbersome. So already we've just got 2 or 3 different types of entities, and we've got 7 different classes here that we've created. And what happens if we want something to have the properties maybe both of a static entity or dynamic entity? Maybe we have a tree that's an enemy, but it's also static, right? So it's really hard to design an entire system like this. And what you're going to end up having is like hundreds of different classes. What if, for example, you want to have a skeleton that has a shield or a skeleton that has a sword? Do you have like a skeleton sword class and a skeleton shield class? It just gets a little bit cumbersome. So we're going to get around all this with entity component model. So in the entity component model, that's the EC part of ECS. An entity is any object in the game. So similarly, this tile would be an entity, the Mega Man would be an entity. What a component then is a property that we can attach to an entity. So what are some examples of those properties? So for example, most entities will have a position. Like this entity here will live at a particular XY location, which is different than this entity's particular XY location. Maybe some entities have a speed, right? So maybe have a bounding box. So for example, Mega Man here might collide with things based on its bounding box, and we'll talk about bounding boxes in the future. Maybe entities have a health. So for example, a tile might not have a health, but the player might have a health, right? So what we can do is then an entity will just become a container that we store components in. And then based on which components are present inside an entity, that's how we write the logic for our game. And I'll have examples of that. So within the entity component model here, how does that example that I gave before look? Well, if we look at a tree, what will a tree have to have? Well, a tree has to have a position, and it has to have a sprite, right? So a tree as a decoration basically just sits there and you draw it. Nothing else happens to it. So you have to draw it at a particular position. So a tree would have a position component, and it would have a sprite component. Let me get the pointer out here. Similarly, an enemy and a player. So how would we design enemies and players in the entity component model? Well, what does an enemy have? So an enemy might have a position. It might have an AI that controls it, right? Like if the player is close, then walk toward it, something like that. It's going to have a sprite, so we're going to have to draw it somehow. It also might have an axis-aligned bounding box. That's what AABB is. We'll have entire lecture devoted to axis-aligned bounding boxes. It might have a velocity because the enemy might move around. And so that would be an enemy, right? Position, AI, sprite, bounding box, and velocity. And now a player is very similar to an enemy, except instead of having an AI controlling it, it would have some sort of input controlling it. So you can see here that this is a much more flat architecture. And what we can do is we can create basically a new type of entity just by mixing and matching the different types of components that we have. And so that's going to be super powerful, and it allows us to create a lot more types of entities with a lot less work. So here we don't need to have a new class for player. We just have an entity that stores those particular components. So ECS for game programming, again, it uses a composition-based design, so composition component. So an entity is anything in the game. Let me turn off this laser pointer. Entity is anything in the game, so player, platform, tile, I've already said that. A component then is a property attached to an entity. So position, texture, animation, health, gravity, whatever. In ECS, components are pure data. Okay, so I want to make this distinction again. I went over this in the first lecture as well. If you look up entity component systems, so I would call that like, oh geez, one second. So if you look up ECS online, more than likely what you'll find is an EC system. Okay, so it's a system that's based around EC, or an architecture that's based around entities and components. That is different than ECS. So in ECS, that is entities, components, and systems. So systems are the code or logic that drives the behavior. In ECS, components are separate from the systems. That's a very important distinction, okay? So we will have a system. Those systems will be passed in some entities, and based on the components, the system will do the logic. In an EC system, which you may find more popularly online, the components contain the logic. Okay, so inside the health component, you would have the logic that updates the health. Inside the transform component, you would have the logic that updates the movement. Inside the bounding box component, you would have the logic that does the collisions. But in ECS, there is a separate system that handles that, and components are just data. So in this course, all the component will store is data, and there are no functions that contain any logic within a component. So I know that's a little bit confusing, but essentially there are two types of entity component game programming paradigms. One is ECS and one is EC. That's what I'm calling it. And we're doing ECS. So just some examples that I said before. Here's some example entities. So for example, we have a player. It might have a position, a speed, a bounding box, a sprite, some health, some gravity. An enemy, instead of, maybe we have, for example, a flying enemy, right? And so a flying enemy might not be affected by gravity, so it doesn't have a gravity component. And rather than be controlled by input, which the player is, the enemy would be controlled by an AI component, which one of our AI systems would then read the details of that component and control the AI. A bullet might have different components, like it might have an angle, it might have a damage component, It also may have something like a lifespan component, okay? So in this case, a lifespan component, what we could do if, for example, we want something to appear on screen for a certain amount of time and then disappear, well, with object-oriented programming, you know, maybe we have to now have a class which implements that, right? So we would have to have a bullet and maybe a temporary bullet that lasts only a certain amount of time. But what we can do with ECS is just have a lifespan component, and that lifespan component would hold like a certain amount of time in it, so maybe 60 frames or 120 frames. And what we then do is in our lifespan system, we say if any entity is alive for a longer duration than its lifespan, then we just kill it. And so, or destroy it. So that way, all we have to do in order to, for example, implement the functionality of a temporary duration on an entity is just give it a lifespan component. And no other logic has to be done. And then we have things like tiles, which are very simple. They may take a position, a bounding box, and a sprite only. So I gave these examples before. So an example now of our movement system up here, our movement system will be a function. So maybe we'll have a function in our game class which just handles movement. And all we have to do for the movement then is say for each of our entities, take the speed and add it to the position, right? So this is actually velocity, but take the velocity and add it to the position. So we have an X and Y component velocity, that is how much we should update the entity every frame. We add that to the position and it's done. With that one line of code, the position and movement of all of our entities is handled. Next, maybe we have something like a collision system. So if we want to write a system that does the collisions, and for example, we want to write the code that says, okay, when a bullet hits an enemy, I want to destroy the bullet and I want the enemy to take some damage. Well, that looks really, really simple now. So what we can do is we can just loop over all the bullets on the screen, and then we can say, hey, for each enemy, if there's a collision between the bullet and the enemy, subtract the bullet's damage component from the enemy's health component, and then destroy the bullet, right? Now, something that's also really easy is what we could do is if we wanted to have, say, piercing bullets that went through enemies, we simply would not destroy the bullet here, right? And so the entity component system makes us really, really powerful in being able to implement game programming mechanics and concepts really, really simply. And then when we go to draw our system, all we have to do is say window.draw, get the sprite component from the entity at the position of the entity. So last time we talked about SFML and how we draw stuff. Well, it's going to be super easy to render our entire game because all we have to do is if an entity has a sprite component, then we do that. So the architecture that we will be looking at eventually, oops, I need to change something. Give me a second. We're doing it live. All right. So this is going to be called a scene. So at the very top level, we're going to have a game engine class. Now this is what it'll look like going forward, right? For our first game, we will not have this architecture because the first game that we create for the second assignment is going to be just getting used to entities and components. So the first game will just have entities and components, and then the second game will have a game engine and this hierarchy. Inside the game engine, we'll live different scenes, and we'll talk about what scenes are, but essentially, a scene of a game is a particular part of a game where the mechanics are similar. So for example, if you've played an RPG, one type of scene might be where you're walking around on the world map, and another type of scene might be when you're inside like a battle, right? So those are the different types of scenes. Each scene is going to have its own type of systems, because the logic is different, right? If you think about it, walking around on the world map, the controls and physics are completely different than in a battle, right? So that's why they would have different scenes. In the scene would live the systems and also something called the entity manager. The entity manager is going to be a factory that is going to contain all of the entity data, and it will destroy and create all the entities for us. The next lecture is going to be all about the entity manager, so I won't go into that too much. And the entity manager is going to hold the entities, and the entities are going to hold the components. And so this is the hierarchy that we're going to be using. And so just to go a little bit further on what is a component. So a pure ECS component is just data. We might have a little bit of logic in the constructor just to set up that data, but there is no helper functionality within the components, okay? If you've used Unity in the past, and I know that they used to use like EC. So for example, in Unity, you'd have a component, but the functionality would be in the component. There'd be functions on that component. And it does make it a little bit different. So a component class has some intuitive meaning to it when an entity contains it. So for example, when you're designing your components, you should separate them such that like game functionality is separated into each component. So for example, gravity, that's a really intuitive type of component to have. So what we can do in a game if we want something to be affected by gravity is we just attach a gravity component to it. And then in our movement system or our physics system, if we want something to be affected by gravity, well, all we do is we say, hey, does this entity have a gravity component? If it does, then we just make it fall down, right, on that frame. And in that way, what we can do is we can do really cool stuff. Like we could have a gun in the game that when we shoot something, makes it affected by gravity. So if we have tiles on the level, and let's say the tiles are just static, and then we shoot them with our gravity gun, and as soon as the bullet hits it, the tile falls. And the only thing you would need to do in the game is just whenever your bullet hits the tile, you attach a gravity component to it, and the rest of it is done for you. So how are we going to implement this in C++? Well, we'll talk about that. So an entity then is any object in the game. There's no unique functionality on an entity, okay? So the only functionality on an entity, which we'll see, is like being able to destroy it. And it just stores components. That's it. So an entity, like in implementation, is just storing components. And it's going to store, at most, one of each component type. So an entity will have, at most, one gravity component. It will have, at most, one position component. It will have, at most, one health component. So let's say, for example, we want to do something where we want a player to be able to hold items, right? Well, what we would have then is we'd have an inventory component, and that inventory component would store multiple items, okay? We wouldn't have a player with multiple item components because we are enforcing, and we'll see why this matters later, that each entity has either 0 of a component or 1 of a component. It will never have multiple of the same type of component. All right, so how components are stored and used within an entity, it can be complex, and later on we'll look into some really complex solutions, but at first let's just look at the first 2 possible things. So what we can do is, because we have said that there's at most 1 of each component type, what we could do then is we could just have a variable for each component type within an entity. And I'll show an example of that in a second. The second thing we could do would be to store a single container of components. And then what we will be able to do is use an add component and a get component function for more generality, right? So let's just look at what I mean by that. So here's the first one, where we can have component variables, okay? So let's say here that we were storing raw pointers, okay? So we have a transform component, pointer, we call that C transform. So again, here's the entity class, okay? All the entity class does is store components. And so here's an example of how we might set up that. If we were using raw pointers, which we won't, and I'll get to that in a second, so we would have, for example, if these were our 4 component types in our game, we could have a transform, a name, a shape, and a bounding box. What we would have is we would just have a single variable for each of those components, okay? And so, for example, we would set them all up to be null pointer at first, because when an entity is created, it has no components attached to it. And so as we attach components, we'll be able to tell if an entity has that component, because its component would not be a null pointer, right? But what we're going to do in this course, we are using shared pointers, okay? We talked about that in the C++ lectures. We are not going to be using raw pointers in this course. So this is much, much, much safer. So what we will have, this is the exact same functionality as this, but just using shared pointers. So our entity will contain, in this example, 4 shared pointer variables. And when you create a shared pointer as a member variable, by default, it will be storing a null pointer, okay? Because you haven't set it up yet. So this is what we will be using for assignment 2, is exactly this. Okay. Now, if we wanted to, for example, the second option would be to store a collection of components. You might think, okay, well, maybe I'll have a vector of component base classes or something like that. And then what would happen is you'd have an add component function with some arguments and a get component function with some arguments. But we'll get back to that later, because that can actually be a little bit complicated. So I'll have like half of a lecture just devoted to that specifically. Okie doke. So in this class, we are going to have a different component class for each component that we want to implement. So the naming we'll have C at the beginning, capital C, and then we'll have component name. So for example, the transform component will be called C transform. If we have a bounding box component, it will be called C bounding box. Health will be called C health. And it's very, very easy to implement the entity component storage using option 1, because all we have to do is, if we have our own class, we just have a shared pointer of that class type for each of the components, right? And that's just how we store them. Okay. And we'll come back to this one later in the course, how we do that. So let's look at an example component, the transform component. So if you're not used to like computer graphics, the transform of something is essentially how it has been moved or how it is planning on being moved throughout the lifespan of this entity. So for example, different types of transforms are scaling, rotation, translation, etc. So basically anything that has to do with the position or the velocity or the size of the object, that's going to go in the transform component. So what we have here is a Vec2, and so this is the transform class. We're going to make everything public. So these could technically be implemented as structs, but I just want to have them as classes. And each of the position, so for example, 2 of these member variables could be the position, so where the object is in the level, right? So the position is going to be here, this is where it is. And then the velocity component is going to say like where I want to be on the next frame. So we would have a default constructor and a constructor that takes in these parameters. So for example, if I want to set up a transform component, I could pass it in a position and I could pass it in a velocity, and it would set those components. Now, a Vec2 is simply a data structure which wraps an X and a Y, and I'm going to have the second half of this lecture is actually on setting up the Vec2 class. So for now, consider a Vec2 is just a vector with 2 elements, an X and a Y. Here's another example. So this is the class C shape, and this is what we will actually be using for assignment 2. So what happens here is we want an entity to be drawn on the screen with some sort of shape. And so what we'll do is we'll just have an entity and we'll attach a shape to it. So what's that going to look like? Well, in assignment 2, I've set it up so that, well, even last time we saw how we can draw any regular polygon with the SF circle shape, right? We can set the number of sides that's drawn with the shape, or the number of points, sorry. And so what we're going to have is that the C shape component is going to store an SF circle shape object. Oops, I've made a mistake in the slide, so I'm going to fix that now. This is supposed to be C shape. I'm just fixing this. Give me 1 second. Okay, so the C-shape component would be really, really simple. All we are doing with the C-shape component is just storing the SF shape, right? This is what components are supposed to be. And so we would construct a default shape, and then we could access that because it's a public variable, and then set parts of that shape. So if we recall now, this is what an entity looks like. We've got shared pointers to all of these types of components, and we can access these components because they're public. So how would we then declare an entity? So now that we know what the entity class looks like, how would we actually program and set up an entity for use in our game? So let's just say we have a main function, all right? And I'm going to have some entities. So I'm going to have a standard vector of entities, call that entities. And now I'm going to have some Vec2, right? These are just X and Y locations. I'm going to create 2 of them. And you can create multiple variables on the same line in C++. I just did this because I want to save space in the slides. So we're going to have a position of 100, 200, and we're going to have a velocity of 10, 10. Okay? Now, what I can do, one way to do this would be to set up an entity. And so this entity, again, this would be a heap allocated, or sorry, this would be a stack allocated entity. And what I can do is say, hey, the C transform, okay, which is a shared pointer, I can call standard make shared to set up the shared pointer, right, to the transform, and then I can pass in the constructor arguments of the C transform. So if I want to set the transform of the entity with these parameters, these 2 vectors, then I can just pass in those vectors, okay? If I want to set, for example, let's say if the entity has a name, then I can set the name of the entity. I can just directly call the variable. So I can say e.cname equals standard make shared cname, and then pass in the constructor variable of cname, which is a string. If I want to set up the shape, then I can say entity.shape equals standard make shared c shape, and then I'll have some arguments, okay? Then, once I've got that constructed, what I can do is I can add that entity to the vector of entities, okay? Then, if I have a bunch of systems, then I can say do stuff with the entities. So this is pretty much the method that we will be using, or some variant of this, for the whole course, is that we set up a new entity object, and then based on whatever logic we want to happen to that entity, we will set the variables of the components of that entity using logic like this. All right? And it's really simple, it's really intuitive, there's no complex syntax for that. So now we have, some collection of entities, or we have a single entity. How do we actually do things with that entity? So let's say we have that do stuff variable, for example. So if we want to do some things to our entity, remember we want to pass in a reference to our entity collection here. So I can say for every entity in the collection, and remember I have to have a reference variable here if these are actual entity objects living in the vector. Let's say I want to set the position of the entity, right? So the entity has a velocity and the entity also has a position. And in order to update the entity's position in the world based on the velocity, all I need to do is for each entity, take its position. So I can say e.ctransform, right? This is a pointer, it's a shared pointer, it's a shared pointer. So I access its variable with the arrow operator instead of the dot operator. And I access the position variable of the C transform component. And what I want to add to that is the velocity variable of the C transform component. Okay, so that's how I update the position of all my entities. I just say take the velocity, add it to the transform. If I want to update the position of the shape, so for example the SF shape, the shape that we draw needs to be somewhere on the screen. So what I'm going to need to do is actually update the position of the SFML shape that I want to draw. And the really simple way to do that, I just say e.shape, e.cshape, access the shape variable, and set the position of that variable based on the position of the transform component. That's it. So the entity transform component stores where the entity lives, and when I want to update the position of the shape, I just say, well, take the position of the transform and set the position of the shape equal to that. And then to draw this to the screen, all I have to do is take my window, my SFML window variable, and call .draw with the shape variable. And that's it. So if I set up some components or some entities, if they have transform components that have speeds, that have velocities, this code is all I need to do in order to update their positions and draw them to the screen in the correct place. 3 lines of code. So that's super, super simple. And you're starting to see some of the power of ECS here. So this might be what we do if we want to put all of our logic in the same place, right? So all of our game logic is here, the updating of the positions and the drawing. But the power of ECS starts to really come in when we talk about systems. So what we want to do is we actually want to have one system that specializes in doing a very specific task, and we're going to break down those tasks by game functionality and game mechanics. So for example, what we will actually have is a movement system. And the movement system will be really, really easy. It will be part of what we just did, but this will be the system that just updates the position. So it does the movement of all the entities. So in this movement system, we pass in the entities, we iterate over the entities, and we add the velocity to the position. And that's it. We're done for movement. It's crazy how simple that is. And similarly, we might have a rendering system, or we talked about systems before, right? So what we could do in our game engine, if we had a movement system and a rendering system, we would first call the movement system, that would update the positions, and then later we would call the rendering system, and that would draw everything. Okie doke. So some systems only operate on entities which contain certain components, right? So not every single entity in our game is going to have the same logic applied to it. In fact, some logic definitely shouldn't be applied to some systems. So for example, the movement component, the movement system will only operate on entities which have transforms. Now it turns out most of the entities will have transforms. The rendering system will only be applied to entities that have both a transform and a shape component. So now we're getting a little more complex. And for example, if we had a physics component, and in the physics component we did things where we detected if 2 enemies collided with their bounding boxes, then the physics system would only operate on things which had a transform as well as a bounding box, right? So what we can do is we can filter entities by we only want our systems to operate on the particular entities that they should based on the components. So there's 2 ways to do that. The first way we could do it is to filter out the entities before passing them into the system. Or another little simpler way is just to check the entities for the required components before using them. So again, just a quick recall. Here's what the entity class looks like, right? So we can access the C transform, the C name, the C shape, all of those directly. So how would we check for a component then? Well, it's really simple. If we have an entity, so we're going to set up a new entity, we're going to add a name component to that entity, right? So this component is stored as a shared pointer. And so if we access the shared pointer variable, if that shared pointer has not been initialized to anything other than its default value, it will return false. So this is really cool. It acts like a component in that, or it acts like a normal pointer in that sense. So here, if I have an entity and the only component it has is a name component, if I say if e.c transform, this will be false. If I say if e.c name, this will be true. Right? So why is that? Well, it's because both C transform and C name, both of those are shared pointer objects. And if a shared pointer object has not been initialized other than default, it will be false because its pointer is a null pointer. So since I have not added a transform to the entity, this will be false. Since I have added a name to the entity, this will be true. Okay? So, for example, in our rendering system, if I want to filter out entities to be rendered, all I have to do is iterate through all the entities, and then I can say, okay, well, if the entity has a transform and it has a shape, then render it, right? But if it doesn't have both of those things, then it won't be rendered. So that's how I can do this. This is how I check for components. And this is exactly what you'll be doing in assignment 2. So now, in the rendering system, what will the rendering system look like? Well, if it gets passed in some sort of entities, again, we're just going to loop over all of those entities. And we're going to say if the entity has a shape component and if it has a transform component, set the position of the shape equal to the position of the transform, and then draw it. And that's it. So that will be our rendering system. And in a more complex game, we may have, for example, let's say we have something like a gravity well that sucks enemies into it, right? That may be invisible. Or let's say we have an entity who can hide itself or not. So you might be able to turn off the shape of that entity. So what this will ensure is that we only attempt to draw things which have a transform and they have a shape. Now, in later assignments, this might be if it has a transform and it has an animation, or if it has a sprite or something like that. But this is the type of logic that our systems will use. Similarly, if we have a system that handles the physics, we'd say something like, if this entity has a bounding box and it has a transform, then attempt to do this, right? Otherwise, if it doesn't have a bounding box, then there's no physics to do on it. Okay, so feel free to ask any sorts of questions. I'm going to take a little drink break here before we get into the Vec2 class that I talked about a minute ago. So someone in chat just talked about, said, wouldn't it be better to have a system of with vectors, those transforms separately, use the entity? Yes. So they're essentially saying, wouldn't it be better if you didn't store the components inside the entities themselves? So that is someone who's probably not in the course, or if they are in the course, good for you. And so this course is designed very specifically to be a good balance between functionality, usability, understandability, and performance. Okay? So for the first assignment, that like everything that we learn will evolve as the course goes on. So for the very first the first game assignment, so assignment 2, this is the architecture that we're using, where an entity it directly stores the components, right? So what we'll do in the next assignment is that the entity will store a collection of components. And that's what we're going to use for the duration of the course. But right at the end, I'm going to get into these sort of super optimizations, and I will have an entire lecture devoted to those optimizations, where we do things like memory pooling, etc., where we store things more cache-friendly in memory. So yes, if you are making a AAA game, this is not how you would store it. But for those of you who are unfamiliar with the course, people in this course haven't even seen C++ before, right? So I can't start the course with memory pooling because that would be a little too difficult to process. Okay, so now we're going to go back to where we were. Someone in the class just asked what that arrow variable was. That's a great question, and I forgot to cover that in my C++ lectures. So what I'm going to do is when I get through these slides, I'm going to be live coding the Vec2 class, and before I do that, I will explain the arrow syntax. So sorry for that. I should have covered that in a particular course. Oh, no problem. I'm responding to people in the chat for those of you who are watching the recording. I love those questions, and I'll only be responding to questions if I have the time to, so no one is ever interrupting by posting a question in the chat. Okay, so now we're going to explain that Vec2 thing and what that was. So vectors in games. Why are vectors important? So for 2D games, so literally at any point in the course where I'm talking about 2D games, we can apply the exact same thing to 3D games. And in 2D games, we'll have an X and a Y component. In 3D games, we would have an X and a Y and a Z component. Okay, so for 2D games, many quantities or properties of game objects have both an X and a Y component, and these form a vector. So when I talk about a vector here, unfortunately, vector means two things. We're talking about a mathematical vector. So if you did Math 2050, I think it is at MUN, which is the linear algebra course, we're talking about that sort of vector. We are not talking about a collection vector, which we also use in the course. So vectors in the mathematical sense, a 2D vector will have an x and a y component. We're not talking about the collection. So for example, we might have a position in our game. So a position is where something would live. That will have both an x and a y component. We might also have a velocity. And so a velocity also has an x and a y component, right? And if all of our 2D variables are going to have both an x and a y component, this is going to be really, really annoying to have to store and refer to and do the mathematics on the x and y components separately. And so what we're going to do is we are going to make our own 2D vector class, and we'll call that Vec2, okay? So before we get into the implementation, just some notes on that. So we're going to go more in depth on actual vector math, like vector addition, subtraction, multiplication, all that kind of stuff, normalizing. That'll be in a couple of lectures. But we're going to first introduce the programming architecture, and then later we're going to use it to do the math and physics, okay? Now, there is, built into SFML, there is an SF Vec2f class. That Vec2f class is exactly what we're going to be implementing ourselves. But we're going to be reinventing it because I want you to truly understand what's going on with that class. Not only that, but we're going to be extending the Vec2 class so that it has far more functionality than the built-in Vec2f class, okay? So if you see Vec2f, so for example, if you take a circle shape object and you say get position, that will return an SF Vec2f object. And so it already exists in SFML, and this may seem a little bit convoluted. And so if we were maybe designing our own game, like to be released, maybe we wouldn't create our own Vec2 class, but for the course, it's a teaching part, right? Okay, so the Vec2 class. What do we want to store inside the Vec2 class? Well, we're going to have two member variables. We're going to have an x and a y object, or variable. What do we want to do with those values? Well, we're going to create a bunch of functions and operators on the Vec2 class. And what those will allow us to do is really easily access those variables and do operations on those variables, which we will need to do very, very frequently. So base things like add vectors, subtract them, multiply, divide. We can take the length of vectors, we can normalize them, we can rotate them, etc. So when we start to get into like these type of operations, these operations are not necessarily there on the SF Vec2 class, okay? So the Vec2 class, it will look something like this. So when we have a class and something like a vector, you probably would say, okay, the x and the y variables should be private, right? We're doing data encapsulation and data hiding. We're doing really good object-oriented programming. But when it comes to a class like Vec2, where we constantly want to be able to really easily get and set the variables of the class, sometimes, and this is one of those sometimes, it's just better to have those things be public, okay? So rather than have a function called getX that returns x, and rather than have a function called get or set y, which takes in a value and then sets y, sometimes it's just easier to have it be public, okay? And despite what your earlier classes might say, sometimes this is just better. And we'll see why it's better going forward. So we can have a base constructor here. So our default values for x and y will be 0. We'll have a base constructor. We'll have a constructor that takes an x input and a y input, okay? And then we'll set those. We might also have an equals operator, a plus operator. And actually, I'm going to go through all of those operators and examples of those in the live coding, which I'll do in a couple of minutes. So how would we use a Vec2? Well, we saw an example of this already. We can set up a Vec2 as a stack allocated object like this, okay? So we'd say Vec2 position, and we give it an x value of 100 and a y value of 200. Maybe then we have a speed, maybe this should be velocity, or an acceleration, right? So then what we could do in our game loop is we can add speed to position. We can add acceleration to speed. We can figure out how far the object moved each frame by calling the length of the speed vector. Things like this, right? So Vec2 will be a really useful class going forward. And now I'm gonna start by doing some sample operations, so you know the syntax of how to do that. And then in assignment 2, I'm going to give you the skeleton code of the Vec2 class, and you're gonna fill that out. All right. So first, before I do that, I'm gonna go a little bit through the chat. So let me get up one of my my talking scenes here. All right. So some questions. Someone talked about some pointer arithmetic. Yeah, I'm gonna show that in a little bit. Someone said, I understand why we are remaking it, but what's technically faster, SFML's Vec2 or the one that we're making? They will be almost identical in speed. So since we're implementing our own Vec2 class, like things like getting and setting the X and Y values and adding them together, they will both be identical. I cannot see how one would be faster than the other unless you did something really, really, really wrong, okay? Because we're just passing in we're passing in base types and we're doing arithmetic on base types. So unless the SF vector is doing something crazy on the inside of it, they should be exactly the same speed. The only difference is that ours will have more functionality. All right. What else? Other stuff talking about some people are trying to help others which don't know the arrow syntax, but I'm about to show that anyway. Okie dokie. Let's get out of the slides and let's get into some programming. Where's my scene for that? Okie doke. Here we go. We are back at the terminal. So I'm going to vim, what is this going to be? lec5.cpp. All right. So I'm programming this from scratch. Haven't done it yet. We might run into some errors or some fun things that are going to happen. But first, what I'm going to do is show that pointer arrow syntax. So we're going to include IOStream as we normally do. Then we're going to have a main function. So int argc char star argv. This is not. There we go. All right. So this will return 0. Now, let's say that I have. Actually, we're going to do the Vec2 class first, and then we can use that to explain the pointer syntax. That'll be good. Okay, so as I said before, if we have some sort of entity and we have an int x and an int y, or int x and y, doing all of our math in this function on separate x and y variables is going to get really, really old really, really quickly. So let's create the Vec2 class, okay? Class Vec2. All right, and we need to have this. Now, everything in this class is going to be public. And Vim likes to indent it for me. So the public, we're going to have a float x, and we're going to initially set that to 0. We're going to have a float y, and initially set that to 0. When I showed it in the slides, I had it on the same line, but I like doing things on different lines if it's possible. I just wanted to save the space in the lecture slide. Then we were going to have a Vec2 constructor. Okay, so this is going to be the default constructor. It's not going to do anything. So if we pass no arguments into a Vec2 constructor, it's just going to create one with 0 and 0. Next, what we're going to do is we're going to have the Vec2 constructor that takes in arguments, right? So this would have, for example, float x in, float y in, and then down here, we would properly use initializer lists, and so we would say x gets the value of x in, and y gets the value of y in, okay? Now, in my components and stuff, this is the same syntax, and I'm going to do this just for some space saving. But usually I do like to put my initializer list variable allocations on different lines. All right, so now what we can do down here is we have the following functionality. We have a Vec2 class, and we can get and set variables in that Vec2 class. So let's call this position, and let's give it values of 100 and 100. Okay? So what I'm going to do up here in the Vec2 class is I'm going to have a print function as well. So this is the cool thing that we can do now is, let's say, for example, in a bunch of places in my code, I wanted to print out the X and Y values. Rather than printing them out manually, I could have my own function which prints them out here. So this is a void function. It returns nothing, and it's const because I don't want it to be able to modify the internal variables. We talked about that already. So here, I'm going to print out standard cout vec2, and then it's going to have the X, and then a comma, and then the Y. And then it's going to have this, and then a new line. Okay, so that print function is going to print it out. All right, so we'll go down here, and I'll just say position.print. So let's see what this does. Should print out vec2 100, 100, and it did. Now, if I say, let me just, I'm going to move this down here like this. Okay, and now vec2 p2, and this will be 300, 400. And now p2.print, just to show you that it'll print those things properly. Okay. I have talked about in previous lectures standard end line, but I need to fit it on one line to make this code look properly. So that has already been covered in the C++ lectures. So for people watching the recording, someone said, why didn't you use standard ENDL, which we talked about before? Okay, if I did want to access the variables inside these vec2 things, I can say, oh, I didn't want to undo that. Okay. So I can directly say p.x equals 1,000. I can say p2.y equals 314. All right. Now if I print these out, these variables will be changed. So here we go. All right. So what do I want to do next? So right here, this is the syntax that someone was asking about before. So let me delete p2. Now, this is, I'm going to change this variable name to pause just to make this a little less. Okay. If I wanted to have a heap allocated position variable, we talked about this before, right? People are asking for bottom right face. Well, usually it's better. Like where I'm typing is not going to be up there. Like all you're missing is a new line, right? But anyway, I'll put it down here for now. Okay, if we want to have a heap allocated vec2 variable, what do? We say vec2 star. I'm going to call this ppos. Okay, so this is a pointer to a position equals new vec2, and now we're going to pass in like 200, 300. All right, so this is going to set up a pointer to a variable. Now, here's the difference. If I want to get access to the ppos, to the pointer to the position, what I have to do, as I saw before, is I have to dereference ppos and then call .x. Okay? So if I set this to 444 and then I say ppos.print, then this will work. Oh, geez. Oops, I didn't wrap that properly. So this is what I would have to do. There we go. I put the bracket outside. All right. So this will work, right? But this is extremely cumbersome. And so this is the only way we know how to do this up to this point. Okay? But the shortcut for that in C++ is the following. We can say ppos arrow, so it's a dash minus sign and then the greater than symbol, and we call it the arrow operator, even though it's two symbols. And then we say dot x equals 5555. And now it'll be 5555. Oops. Sorry, not dot x, it's just this. Now down here, what I could say is ppos print. Okay, so this, dereferencing the pointer and then calling dot, is identical to just using the arrow operator. So the rule is, whenever we have a stack allocated variable, it's just a variable pointing to something, we say dot x. And if we have a pointer to something, we say arrow x. Okay? And similarly, in this course, undo that. If I include, by the way, you can have include statements wherever you want. It's just nice to put them all at the top. So let me not be bad and let me put it up here. Include memory. Okay. If I have a standard shared pointer to a Vec2, and I call that, this is the shared pointer position, SPP. This is equal to standard make shared Vec2, and then I can give that the parameters the same way. Okay, so when I have a shared pointer, it is the same syntax as a raw pointer. If I want to get access to SPP's x variable, you would say SPP arrow x. If I want to print it out, I would say SPP arrow print. Okay? That's it. So that's how we would use the shared pointer as well. Whenever we're referring to a stack allocated variable or a local variable, we use dot. And whenever it's a heap allocated variable or a shared pointer, it's arrow. So that's what someone was referring to before. So let's now try and add two vectors together. So we have position 1 and we have Vec2 position 2. And this might have like 300, 500. So what I want to do is say Vec2, let's say position 3 equals pos1 plus pos2. Well, if I want to just create this, right, I can do it manually. I can say pos1.x plus pos2.x, pos1.y plus pos2.y. Now that is very, very cumbersome, okay? We don't want to have to do that every time. What we want to be able to do is say this is equal to pos1 plus pos2. So if I just try and run this now and say pos3.print, what will happen? Well, it says the following. Error, no match for operator plus on Vec2 and Vec2. So in this line, when we tried to use the plus operator on the object of type Vec2 and the object of type Vec2, there is no plus operator that exists. So here is where C++ gets super powerful, okay? And you literally can't do this in Java. Now, whether that's a good thing or a bad thing, you can argue that, but it's not something you can do in some other programming languages. Unless a new version of Java has let you put in operator assignments. Okay, so what we want to be able to do here is use the plus operator to take in two Vec2s and add them together. So yes, to the people in the chat who are saying what I can do, this is me teaching a class, right? I obviously know the answer. I'm just building suspense, as someone else in chat said. So the syntax for that, we saw last time when we made an int array, we had the operator of the brackets, but now we're going to do this. Okay, so I want the plus operator to return a new Vec2 object. So this is going to be a Vec2 object return, and it's going to be operator plus. And what's going to happen in here is we want to take in, essentially, another Vec2. And I'm calling this RHS because it's the right-hand side variable, okay? This, I don't want it to be able to modify the function, and so I'm saying that this function is const. So again, this syntax says this function is going to return a Vec2. It's going to be the operator plus that we're overloading, as an argument, it's going to take in the right-hand side Vec2. So if I scroll down here, it's going to be the pos1 operator that we are calling the plus operator on, and the pos2 variable will be the thing that gets passed in as the variable, okay? Now, as we said before, typically what we want to do is pass in things that aren't primitive types by const reference, right? So we'll pass that in as a const reference. And the reason we're returning a copy of this vector is because it's going to live on the stack, so we're returning a copy of it. So what we want to do, we can one-line this. We can say return vec2, and we're going to add my x value to the x value of the right-hand side argument, and we're going to add my y value to the right-hand side's y value as well, okay? And so what this does is it creates a new vec2 object, and it creates it by adding the current object's x value to the other operand's x value, and the current y value to the y value. Okay, so now if I compile and run this, it works. So we took 100, 100, and we plussed 300, 500. Look at that. That's great. Okay. All right. Now let's say, for example, I wanted to just add a value to the pos1 variable itself. Okay? So, I could do something like if I wanted to change pos1. So for example, now I could say pos1 equals pos1 plus pos2. That will also work, right? So it takes pos1, adds it to pos2, returns a vector, and then copies that into pos1. That's what's happening here. But maybe what I would want to happen is, for example, I could have here like an add function, right? So normally what will happen here is you can have an add function. So you're going to take in another vec2. That's going to be the right-hand side. Now this isn't const because we're going to change it, right? So I could say my x variable equals or plus equals RHS.x, and my y variable plus equals RHS.y. And down here, if I wanted to just add something to one, then it would be far more convenient to just say pos1.add pos2. Okay? Now, we can also do that without the add variable by defining the plus equals operator. So, vec2 operator plus equals const vec2 RHS, and we don't want to have this const. Oh, this isn't vec2, this is void, right? Because it's adding it in place. And we can have the same thing where x plus equals RHS.x and y plus equals RHS.y. Now if we go down here, instead of calling this function, we can use it like a normal base type. So I should be able to do this. Yes. And that is much more efficient than taking one object, adding it to another object, creating another variable, and then returning it. So if I wanted to be able to use minus equals, I wanted to use plus equals or times equals or whatever, then I can do that. Now, so far what we've been looking at is we've only been looking at operators on vec2 that take in another vec2, right? But let's say, for example, that we wanted to scale a vec2. So by scaling, I mean we want to make the x and the y both bigger by a certain amount. That's called scaling. So what you have to do in order to scale something is, let's say we have a scale value of 5, and we want to apply it to pos1. Well, if we wanted to do that manually, we could say pos1.x equals pos1.x times 5, and pos1.y equals pos1.y times 5. So that's a scaling operator, right? So in order to avoid all of that, what I can do up here is something really cool, is I can define an operator that takes in one vec2, but not another vec2. So this operator, let's say I want to be able to multiply one vec2 by a scalar and then return another vec2 object. So this is going to be just like the plus operator, in terms of syntax. So I'm going to have the multiply operator. But we're not going to be multiplying two vectors together. That doesn't make mathematical sense, right? We're not doing a dot product here. We are doing a scaling operation. So if I do the times operator, what I'm going to take in here as the argument is a float. Okay, this is const because I'm not modifying the current variable. And then what I want to do is return vec2, and I'll have x times scale, y times scale. So this is a way that we can define an operator that doesn't operate just on types of itself. So down here, what I can do, if I want to scale position 1, right, I can say pos1, or let's do a separate variable, right? So pos2 equals pos1 times 5. And then when I print pos1, oops, I want to print pos2. There we go. So now it's 500, 500. So in this case, I can multiply the vec2 by the star, or sorry, by the 5 with the star multiply operator. Now, here's the interesting thing, which makes things just a little bit complicated, but in order to do this, the variable that gets passed in for the scale is the right-hand side of the operator, okay? So if I go down here, this works fine because this operation, the 5 is the scalar and it's the right-hand side of the operation. But if I do this, where I have 5 times pos1, this won't work because the int type cannot be multiplied by a pos or a vec2. So it really sucks that happens, but it's just like calling a function, right? I can say vec2.add 5, but I can't say 5.add vec2, right? So just like you're calling a function on an object, that is what an operator is. So you have to observe the correct ordering of those operators, right? Now, if I wanted to add two vectors and say pos1 plus pos2, I could just as easily say pos2 plus pos1 because they're both the same. They're both the same type of variable, right? So the right-hand side is always of the correct type. Now, here, another thing that I could do if I wanted to say, for example, return the length of this vector. So the length operation in here is where you'd use Pythagoras. Okay? So you have an x distance, and you have a y distance, and you're trying to compute the distance between those two. So I don't want to do that here because that's part of the thing that we'll be doing on the assignment. All right. So this is how you would use the Vec2 class, and this is why it's going to be so powerful in our course. Now, I had a question. Exactly asks a question and says, so could you make a plus operator overload that allows you to add our Vec2 to SFMLs? Absolutely. And we just saw how we just saw how we could do that. So similar to how I do that with the star operator here, I could have a Vec2 operator plus, and in here, I take a const SF vector 2f, right-hand side, and make this const, and then I would add that x to my x and return a new Vec2. But again, I would only be able to say my Vec2 plus an SF vector 2f. I would not be able to say an SF vector 2f plus my Vec2 because the order of the operations matter. Now, also something that's interesting, and actually I'm not going to get into that in this class, is how we could implicitly convert between types. So here's something that's going to happen, which is going to be annoying, and we will do this a little bit later. So let's say we have a draw function, and this draw function, so void draw, is going to expect SF vector2, or no, not draw, but let's say we have a set position. And so the circle shape, for example, in SFML is going to have a set position variable function, and we're going to need to be calling that. It's going to be expecting an SF vector2f variable as the input. So if down here we call set position on pos1, it's going to complain because we are calling this with a vec2 instead of an SF vector2f. So what we can do inside our vector class is we could have something up here where I define a is it implicit conversion, default conversion? I'm not exactly sure, but we could have SF. So this would return SF vector2f. Okay, so it would create a new one. And this is operator. And we'd have this. I believe this is the syntax. So I can't compile this because the system that I'm on right now, telnetted or SSH'd into, doesn't have the SFML library. But it would look something like this. Const. And down here, we would return SF vector2f x, y. So what this does is wherever we wanted to pass in at SF vector2f, because we've now defined a conversion. So for example, if we had a function that took in an integer, but we passed in a float, C++ would automatically convert it. It might show a warning, but it would automatically convert it via truncation or rounding or something like that. So this defines the fact that, hey, now our vec2 can be converted into a vector2f. Okay, so this might not be the exact syntax. We'll be getting into the exact syntax later, but this is how you would do that. And then down later, when you call set position, you'd be able to call it with a vec2. Okay, so that's it for this lecture. So we've now gotten to this point. The next lecture is going to be an entity manager. This is a really cool lecture. I really like this one. So we're going to see common problems that arise during game programming, and we're going to see how an entity manager factory, which handles all of our entities for us, can be a really, really good thing. All right. So we're also going to go over some vector math and talk about circle collisions, and by the end of this assignment, you'll have everything that you need to know for assignment 2. And assignment 2, we're essentially making a Geometry Wars clone, and actually, let me show that for people who are new. I think I have a solution up and running somewhere. Not there. Give me 1 second. I really want to show this. Okay. So here is the game that we're going to be making for assignment 2. We're going to have this character in the middle here. This octagon is us. And wherever we click on the map, it's going to shoot a bullet, right? So this is how we're going to learn ECS. All of this will be done with ECS, with the entity manager, with the Vec2 class, etc. So we've got a little guy here. This is me. If I run into an object, it's going to destroy me and put me back at the center. It's actually going to destroy the object as well. Whenever we shoot an object, it's going to destroy that object, and it's going to spawn baby objects, which are half as big, and it's going to spawn them with the same color, and it's going to spawn as many of them as the original object had sides. Okay? And next class we'll talk about all the stuff that we need to know to implement this. Oops, tabbed over. And this game is going to have a configuration file here, which allows us to do things like set the size of the player, the bounding box of the player, and also, for example, the enemies, the spawning time. If I change that down to 200 milliseconds instead of 2 seconds and then rerun this, then things are going to be spawning 5 times a second, right? And things are going to be way, way bigger, and everything's going to be in the config file, and I can't remember what any of the other options are. Oh, I think this is the bullet size, for example. So if I rerun it like this, then we have gigantic bullets, and the game becomes really, really easy, right? We're also going to see that our bullets fade out over time. So we're going to talk about like a lifespan and how we can do that. And so there's lots of cool stuff that are in assignment 2. And, you know, this is an actual game now. So the second assignment will be an actual game, and you'll see just how easy it is going to be going forward making these types of games. So that's a little teaser. We just did this lecture. Next time is the entity manager, and then we're going to be making that game and describing that game in assignment 2 on this lecture. That config is kind of annoying to edit, someone says. Well, I mean, editing a text file is as basic as it gets. So I don't think it's annoying at all. What we're trying to show via config files is that you can hand the game engine over to a game designer, and the game designer can tweak the config file to make the game as easy as hard as they want without being able to read the code. So there's no more questions in the chat right now. We are starting to really get into the course, and it's going to be pretty cool and exciting going forward. One last comment here in the chat. Some people said, oh yeah, we could use XML. Yeah, we could use JSON. Or we could not, because this course is not about spending hours and hours teaching students how to use C++ JSON parsers. It's about just reading stuff in and making games. So all about making games, and the rest of the course going forward is going to be making games. All right. See you on Tuesday, and if you have any problems with assignment 1, don't be afraid to contact me, but don't leave it until the last minute either. All right. See you later.